Aloha BIOCHEM. In this video we continue in Chapter 2 and discuss isotopes. Hello again. This time we cover Section 2.3, Isotopes. Let's begin by recalling what we did in our previous lecture. Then we discussed atomic structure. So what is inside the atom? What are the three subatomic particles? And we saw what makes atoms of a particular element different than those of another. One of the examples that we looked at was lithium. So here's a model of a lithium atom. Now lithium is element number 3, and that's called the atomic number of lithium, and that tells us that all lithium atoms have 3 protons. You remember the protons and the neutrons are in the nucleus, and the electrons surround the nucleus in what's called the electron cloud. The protons and neutrons are much heavier than the electrons are, and also the protons have a positive charge to balance out the negative charge on the electrons. Neutrons do not have charge. They are neutral in charge. So that's what a lithium atom looks like. And all lithium atoms have 3 protons, and anything with 3 protons we call lithium. Now, we asked the 2 questions. Do they all have 4 neutrons, like is shown in this example over here? So here I see 4 neutrons and 3 electrons. So do they all have 4 neutrons? And do they all have 3 electrons? Well, in the next chapter we will discuss the situation where atoms can gain or lose an electron. And then the charge is no longer balanced, and we call such particles ions. So lithium, for example, tends to lose 1 electron. And when it's missing one of its negative charges, it has extra positive charge. And so the atom is no longer balanced, and so we call it a positive charged ion. So that's coming next chapter. In this lecture, we take a look at the case of the neutrons. So we'll see that for many elements, although you cannot change the number of protons, that identifies an atom of a particular element, the neutrons can vary. So for instance, hydrogen atoms, they all have 1 proton because hydrogen is element number 1, and the balanced atoms all have 1 electron. But as far as the neutrons go, some hydrogens have 0 neutrons, some of them have 1 neutron, and even some have 2 neutrons. So atoms of a particular element can vary in the number of neutrons that they have. These are called isotopes. So isotopes, as explained by the author, I've quoted Janice Smith's definition or description. 2 atoms of the same element always have the same number of protons, but the number of neutrons can vary. Here's the definition of isotopes. Isotopes are atoms of the same element having a different number of neutrons. This is an example right here of the 2 isotopes of chlorine. So chlorine, let's locate that on the periodic table. So here's the periodic table again, and chlorine is over here. It's the 17th element. So you go across 1, 2, then 3, 4, 5, 6 to 10, then 11, 12, and eventually you get to number 17, chlorine. So here's the box representing chlorine. We can see chlorine is element 17, and that's the atomic mass, which we'll talk about later. But because chlorine is element number 17, chlorine atoms must have 17 protons. And balanced atoms of chlorine will have 17 electrons. But some chlorine atoms have 18 neutrons and other ones have 20 neutrons. It turns out that most of the chlorine atoms that you'll come across have 18 neutrons, but some of them will have 20 neutrons. In fact, in any sample of chlorine that you come across, there's always a mixture of these two isotopes of chlorine, and 76% of the atoms will look like this on the left. They'll be the lighter of the two with only 18 neutrons, and then the remaining 24% will look like that. They'll be the heavier ones with the 20 neutrons. Now we can call these isotopes chlorine 35 and chlorine 37. The 35 and 37 is really telling us how many particles total are in the nucleus. So 18 neutrons plus 17 protons is 35, and so we call that one chlorine 35. And this one has 37 particles in the nucleus, so we call that 37. Now, another way to represent these two isotopes is by the isotope symbol. So this atom of chlorine, this particular isotope, has the following isotope symbol down here. You put the element symbol, and then at the bottom left, you place the atomic number, which is the number of protons, and then at the top left, above it, is the mass number, which is the number of protons plus neutrons. So this one has 35 particles in the nucleus. We call that the mass number because these are the particles that are basically representing all of the mass in the atom. Remember, the electron mass is almost insignificant compared to these two. These two overwhelmingly represent the mass of the atom. So this particular atom with 17 protons and 18 neutrons has 35 massive particles. And the other one has 37. So the other isotope symbol looks the same except for the mass number. So every isotope you can write a corresponding isotope symbol. Now, here's an example. Given these two isotope symbols, for each of those atoms give the atomic number, the mass number, the number of protons, neutrons, and electrons. So you can pause the video if you like and see if you can answer that question. All right, let's look at the solution. So for those two isotope symbols, the atomic number is simply the atomic number of the element. Now, carbon has an atomic number of 6, and bromine has an atomic number of 35. And you can find this information on the periodic table. So I'll point you to carbon. All right. Carbon's atomic number is 6, and bromine's atomic number is 35. Now, really, these atomic numbers don't have to be included in the isotope symbol. They're sort of redundant. Anytime you see carbon, of course its atomic number is 6. So sometimes you'll see isotope symbols without the atomic number explicitly written. So that's the atomic number. Now what about the mass number? Remember, the mass number is the number at the top left. And for these two, carbons is 13, and this one, bromines, is 79. Now, the mass number represents the protons plus the neutrons, whereas the atomic number just tells us the protons. So with this information, we should be able to figure out how many protons, neutrons, and electrons are in both of those particles. So the atomic number is the number of protons, so we can just take that and copy it over. That's the number of protons. And the same thing for this one down here. That's the number of protons. And the number of neutrons we can get by taking the mass number and subtracting the atomic number. So 13 minus 6 gives us 7 neutrons, and then 79 minus 35 gives us 44 neutrons. And then remember, unless you're told otherwise, the protons always balance the electrons. So the positive protons will balance the negative electrons. In the next chapter, we will talk about ions, where the electrons can be a little bit different than the protons. Now, there is something called the atomic weight, which is listed in the periodic table. Let's take another look at the periodic table. So here's the periodic table, and if you zoom in on any one element, say chlorine over there, chlorine is element 17. Its atomic number is 17, and its atomic mass is 35.453. The atomic mass tells you basically how heavy a chlorine atom is. But the thing is, there are two main types of chlorine atoms. Chlorine comes in two isotopes. Some of them are lighter and some of them are heavier. You remember, we just discussed chlorine isotopes. Some of them are the 35 isotope and some of them are the 37. And most of them, about 76% of them, are of this type. So how can we say what is the mass of a chlorine atom when there are more than one type of chlorine atom? Well, what the atomic mass is it's called the atomic weight as well. What it is it's the weighted average of the mass of the naturally occurring isotopes of a particular element, and it's reported in atomic mass units. So let's explain what this means. It means that if you go back to the two isotopes of chlorine, okay, this one is a little lighter. It weighs a certain number of atomic mass units. It's going to be pretty close to 35 atomic mass units because the protons and the neutrons weigh approximately 1 atomic mass unit and the electrons are almost massless. So atoms that look like this weigh about 35 atomic mass units, but the other type of chlorine atom weighs about 37 atomic mass units. So, what's the average mass of a chlorine atom? It's going to be somewhere between 35 and 37. So think about, the case where people ask, what is the number of children that the average American family has? Well, the American family on average has 2.5 children. Okay, some families have 1, some have 2, some have 3, some have 4, but the average is a weighted average. So no particular family has 2.5 children, and likewise, no particular chlorine atom weighs 35.45. They either weigh about 35 or about 37. This is like the average weight. If you were to look at all chlorine atoms, most of them are the 35 isotope. Some of them are the 37 isotope, and you could ask, well, what's the average mass? Okay, let's talk about how we actually determine the atomic mass of a particular element? Well, here's the chlorine periodic table box. So the atomic number and the atomic mass. How do we get the atomic mass? How is it determined? It can be calculated if we know the mass of each isotope of chlorine and also the abundance with which each isotope occurs. So chlorine comes in 2 isotopes. If we know exactly how heavy the 35 isotope is and exactly how heavy the 37 isotope is and what the abundance of each one is, remember it's about 76% of the chlorine atoms are the 35 and about 24% are the 37. If we know that to a little bit more precision, then we can calculate what the atomic mass is. And so the way you do the calculation is as follows. The 35 isotope weighs more precisely 34.97 atomic mass units. Remember, the mass is always going to be pretty close to the mass number. And the 37 isotope weighs about 37. It's more precisely 36.97. Now the abundance, to a little bit more precision, is 75.78% and 24.22%. So given this information, we can calculate that atomic mass. What you do is you take the atomic mass of each isotope and you multiply it by the decimal abundance, the fractional abundance of, and then you add up the result. So here's the calculation. We take these atomic masses, we multiply them both by their fractional abundance. So you have to convert the percentage to a fraction by moving the decimal point over. So here we go. And doing the multiplication first before the addition, this comes out to 26.5003, and that one comes out to 8.9541. And then you can add these two together, and you see it comes out to 35.4544. With sig fig rules, it rounds to 35.45. And that's where that number comes from. Now, this is the average chlorine atom. That represents your average chlorine atom. Remember, no particular atom weighs that much, just like no American family has 2.5 kids. But this is your average chlorine atom. So let's take a look at a few more examples, and then we'll do something a little different before the end of the lecture. Here are some multiple choice problems, such as you might find on a quiz or an exam. The first one, copper has 2 naturally occurring isotopes, copper 35 and copper 65. Which is more abundant? This is a nice little tricky problem if you haven't seen one like that before. So I'll give you a moment to think about it. You can pause the video. I'll give you a clue. You might want to have a look at copper on the periodic table. Okay, look at the atomic mass of copper on the periodic table, and that should clue you in as to which one is more abundant. Let's talk about how to do the answer, or how to get the answer. So finding copper on the periodic table, it's over here. Copper, silver, gold, they're all in the same column. In the next video, we'll talk more about the periodic table, and elements in the same column are kind of similar in some respects. So here's copper right there. It's element number 29, and the atomic mass is 63.55. 63.55. All right, that's your clue. Now, the copper 63 isotope weighs about 63 atomic mass units, and the copper 65 isotope weighs about 65 atomic mass units. What does the atomic mass of copper look more like? Does it look more like the 63 or the 65? Which one is it closer to, is what I'm asking. Well, it's closer to the 63 isotope. And so the answer for this question is this one's going to be more abundant. The 63 isotope will be more abundant than the 65 isotope. If you go back to our chlorine example, you see chlorine 35 was more abundant than chlorine 37. And so the atomic mass of chlorine is going to be closer to that of the 35 isotope. All right, and that's the similar case for copper. So copper, copper is, the atomic mass is closer to 63, so there will be more of the 63 isotope. All right, let's look at the next example. Boron also has two naturally occurring isotopes, boron 10 and boron 11. And you're told what the mass of the isotopes are. Which one of these is more abundant? Boron 10, boron 11, or both are about equally abundant. Again, you should look at the periodic table. Okay, so let's check it out. Let's find boron. Boron is element number 5, and it's right up here. Okay, element number 5. Now, its atomic mass is 10.811. Now, 10.811 is actually closer to the 11 isotope's mass. So this time, the heavier one is more abundant. So the answer is B. In the last example, which of iodine's isotopes is more abundant, iodine 79 or iodine 81? Let's find iodine. Iodine is element 53, so there it is. And you can see its atomic mass is 126.90. Now, 126.90 is about 126.90. Oh, you see, this time you're not told what the mass of either of these two are. Oh, this is, I made a mistake here. This is supposed to say bromine 79 and bromine 81. That's what's going on. I was a little confused. So dagnabbit. I made a typo here. Okay, so let's see if we can just wing this. So imagine this problem says which of bromine's isotopes is more abundant. Bromine 79 or bromine 81? Okay, so here are the three choices: bromine 79, bromine 81. Sorry about the mistake. And when you find bromine on the periodic table, there it is. You see its atomic mass is 79.9. Now 79.9 is approximately halfway between 79 and 81. 79.9 is roughly 80, and this isotope weighs about 79 atomic mass units. We're not given its atomic mass or the mass of this isotope, and we're not given the mass of that isotope, but we know that they're going to be close to 79 and 81, just like this one was close to 10 and that's close to 11. So although we're not given the mass of each of these isotopes, we can still answer this question because the atomic mass of bromine, again, is 79.9. That's about in the middle. That's about 80. Okay, so this time I'm going to say that they come in about equal abundance. Okay, bromine 79 and bromine 81 are roughly equally abundant, and that's actually the case. About 49% of the bromine is the 79 isotope, and about 51% is the 81 isotope. So those are three interesting questions, and you might want to study up on those. You might see something similar on the quiz or exam, possibly both. You're going to see something on there, in fact. Now, the last topic in this lecture concerns isotopes in medicine. When we get to chapter 10, we'll take a closer look at this in much more detail, but for now, let's provide an overview of how they can be used in a certain example. Isotopes of an element are chemically identical. They form the same types of molecules. So although a particular isotope may have different number of atoms of another isotope, the two will behave the same way chemically. They do the same chemical reactions. They form the same types of molecules. You know, a molecule doesn't know whether the chlorine atom in there is a chlorine 35 or a chlorine 37. It will do the same thing regardless. Interestingly, certain isotopes are radioactive, meaning they will emit high energy particles. So certain isotopes do this. Other ones are normal and are not radioactive. Now, the radioactive isotopes can be taken advantage of and have both diagnostic and therapeutic uses in medicine. As an example, let's look at the two isotopes for iodine that are listed here. The normal form of iodine is iodine 127. So this is a non-radioactive isotope, but a radioactive isotope of iodine is iodine 131. Here are models of the two types of atoms. Iodine 127 contains the following subatomic particles. Let's find iodine quickly on the periodic table. It's element 53, so there it is down there below bromine. So iodine is element 53. So all iodine atoms have 53 protons, regardless of which isotope. And balanced iodine particles have 53 electrons. It's the number of neutrons that differs in these two isotopes. And to get the number of neutrons, you take the mass number, subtract the atomic number, and over here that equals 74. And then 131 minus 53 is 78. So you see this one has 4 extra neutrons, and somehow that makes it radioactive. This is, in other words, like an unstable type of iodine atom, and it has a tendency to emit high energy particles. So if you imagine a pile of normal iodine sitting on the table, there it is. You can scoop up the powder. You can do whatever you want with it. And here is some iodine that contains a little bit of the radioactive isotope in there. Maybe not all of it. Maybe just a small portion is mixed in there. But if you have some of the iodine 131 in here mixed in, then the whole pile you can say is radioactive, and it's emitting these high energy particles in all directions, really. You know, and these particles can travel through material depending on what type of radiation it is. And this radiation can be used in medical diagnostics and also medical therapeutics. So in the body, iodine is used by the thyroid gland to make certain iodine-containing hormone molecules. And these are used all throughout the body. So I'll show you a picture of the thyroid gland. Here it is. The thyroid gland is up here. And what it does is, when the brain tells it to, it makes these hormone molecules. So it makes 2 different types of hormone molecules. The main one is called thyroxine, and you can see a model of thyroxine. It contains 4 iodine atoms. You can see the big purple iodine atoms. And this hormone molecule, as it's made in the thyroid gland, then enters the bloodstream. It travels all throughout the body, and it helps with many different types of metabolic processes. It basically, is involved in pretty much every cell in the body. So if this molecule isn't made on time, in the amounts needed, then that disrupts all of your biochemistry. So the thyroid gland is very important. You need a healthy thyroid. It needs to be able to produce these hormone molecules, on time in order for the body to be healthy. So the thing about radioactive iodine is in low amounts, the radiation isn't really damaging to the surrounding, thyroid. You see, when you consume foods, the iodine in those foods, through the small intestines, it gets into the bloodstream, and it eventually ends up in the thyroid, which is where it's actually used. And if you have a little bit of radioactive iodine in there, it's not going to damage your thyroid. And the radioactive iodine can be observed with special cameras. And perhaps you've heard of thyroid scans. And the way a thyroid scan works is the patient is given a small dose of, a little shot, or somehow, I don't know, what these shots look like, but, a little bit of liquid containing iodine, and there's a certain amount of radioactive iodine in there. And so when the patient drinks that, it gets absorbed in the bloodstream and gets, into the thyroid, and it saturates the thyroid. There's iodine everywhere inside the thyroid. The good normal iodine, and then the radioactive iodine. And then if you have a camera sitting off to the side, which is able to detect these radioactive particles, you can take a picture of the thyroid, that's under the skin. So basically, the radioactive iodine has saturated the entire thyroid, and you can take these nice images, and I'll show you a picture of a thyroid scan. So here's a figure 2.4 in your textbook. You can see this is a thyroid scan, and it is for a healthy thyroid. You can see, the radioactive iodine showing up on the camera, and you have about the same amount over here as over there. So, the iodine is distributed evenly throughout the thyroid. This is a good, healthy thyroid. But over there, you see it's asymmetric. You got, more iodine over here, way more, and then a little bit less over there. So this is a distorted thyroid. This represents something bad going on. And so, thyroid scans are very useful in that respect. You're able to use this radioactive substance to take a picture of your thyroid because it shows up on special cameras. So that's a diagnostic use. Now, when the patient is given larger doses of radioactive iodine, it can actually be damaging to the surrounding tissue. And as it gets into the thyroid, if there's a larger amount of radioactive iodine, what it will do is it'll just start destroying the surrounding cells. This can be beneficial in certain circumstances. So maybe if you have an unhealthy thyroid and then you want to treat it, well, you can do radiation therapy, and if patient has radiation therapy, then the cellular tissue can be changed. So the radioactive iodine can, say, kill some bad cells that are unwanted, and hopefully that'll reshape the thyroid. And doctors do things like this quite often. So in larger doses, the radioactive iodine can go in there and start killing certain cells, but you don't want to take too much. You don't want to kill everything. You just want to kill the bad stuff. And so that's what radiation therapy is. Lots of radiation is dangerous. It kills cells, but sometimes you need to do that. So radiation therapy is a little bit different than chemotherapy. We'll compare the two. Radiation therapy uses radioactive material to kill cells. Chemotherapy uses some other chemicals to stop chemical reactions from happening, which kill cells. And we'll talk about that later on. And when we get to chapter 10, we'll see a lot more uses of isotopes in medicine, but this is a pretty interesting one. So in the next lecture, we will go into the periodic table of elements. So stay tuned for that. Aloha.